this isn't really normally part of the lecture, but I'll throw it in anyway. Let's go back to the mean value theorem for a second. Okay, remember, you have this thing, mean value theorem, right? You have a function, and it's continuous on A, B. It's differentiable on the interior, and then something happens, right? Something happens. Remember, right, you see you have some function, right? It's continuous on an interval, it's differentiable on the interior, and then something happens, and that something is that there's some point where f prime c equals 0. Right? There's some point where the slope is 0. Right? You guys remember that. The question I asked the class at that time was, suppose you have two functions. Okay. Suppose you have two functions, and they differ by the same distance. They differ by the same distance. Right? You got two functions. They differ by the same amount at the endpoints. Right? So at A and B, right, f of A minus g of A, and oops, that's B. Sorry. F of A minus g of A and f of B minus g of B with the same distance, right? And I said, so what can you say? What can you say about this? The thing was that the conclusion was that then there exists a point in C. There exists a point C in AB where the slopes were exactly the same. Okay. Yeah, Rachel.
Is it when you wrote down Rolle's theorem? Because this is a mean value theorem. Theorem say f prime of c equals f of b.
Oh, I'm sorry. Sorry. F of b minus f of a over b minus a. Thank you, Rachel. Yeah. Okay. So there was this other thing that this was the question that I asked, and I think Alfred answered it. Do you remember this? Everyone remembers this? Right. And do you see why that happens? So again, it's the same thing. You know, f and g are continuous in B and differential on the interior. And then if you look at the difference of these functions, right? If we look at the difference function, d of x being f minus g, right? What do you see about that function? Well, you know, d of a equals d of b. Are you guys following? This is actually just this is not really part of the lecture. I'm just throwing this in to hopefully shock you a little bit, or hopefully teach you something a little bit. So maybe if you're not following, I should either give up or make it more dynamic somehow. Okay. So basically, okay. So what should I do? Should I give up? No. Okay. Some people are shaking no. That encourages me. Okay. So I asked. Right, so I asked this question. Right. You have these two functions, and they do something, but the difference at the end is the same. The difference at the end and the difference at the beginning is the same. And so what you do is you say, well, look, consider the difference. D of x being one guy minus the other guy. You notice that the difference at the beginning is the same thing as the difference at the end, right? Difference at the beginning is the same as the difference at the end. And so what does that tell you? By Rolle's theorem, what does that say? If at the beginning and the end they have the same value, then at some point in the middle, The slope is 0, right? At some point in the middle, d prime c is 0, right? But d prime c being 0, what does that tell you? D prime of c is 0. In other words, what does that tell you about f and g? F prime and c prime are the same. F prime and g prime are the same. Right? Okay. So this was the question, and the answer is, what happens if? So the question is basically like this: if you have two cars and they start off 1 mile away from each other, and then they do whatever they want for 1 hour, and at the end of that hour, they are again 1 mile away from each other. Then, mysteriously, or not so mysteriously, then you know that at some point during that hour, they must have been traveling exactly the same speed. Right? That's what this is saying. If you have two cars that start at the same distance, start at a certain distance apart, and end at a certain distance apart, then at some point during the time, their speeds must have been exactly the same. Okay? Yes, Emily?
Thinking about a car, what if one is traveling like 1 mile an hour and the other one just does like 100 miles an hour with this crazy like zigzaggy thing?
Mm-hmm.
How can that work?
At some point, their speeds must have been exactly the same. Perhaps at the beginning, while the car was accelerating up to 100 miles an hour, and the other car is accelerating to 1 mile an hour, their speeds would have crossed.
What if it just starts at 100 miles an hour?
It starts at 100 miles an hour.
And then it ends also at 100 miles an hour, and it's constantly 100 miles an hour, and the other one's constantly 1 mile an hour.
Well, then they're not going to end at the same distance apart.
But if it's like crazy loopy, then wouldn't it? Couldn't it?
So you're saying that your car goes 100 miles an hour from the other car goes 1 mile an hour,
Yeah.
right? And it stays at 100 miles an hour.
The whole time.
The whole time, okay. Right? And then this car goes 1 mile an hour the whole time. How are they going to end at the same distance?
It doesn't have to be a line, does it?
No. But if it's going 100 miles an hour exactly, it is a line.
It's going around the racetrack.
Yeah, if one of them is like,
Oh, I see.
Yeah.
No, they have to be, I see what you mean. So it has to be on a linear track. They have to be on a linear track.
oh, so if you were graphing it, it would just, okay.
Yeah, they have to be on a linear track. So this is each car, right?
Highway.
So you have one car. Sorry, that's yes.
Okay, that makes a
You
lot more
have,
sense.
you have two cars, and their vertical distance is the same.
Yeah.
They're allowed to go like this, as much as they want, and at the end, the distance between them is still the same. The
Wait, so
vertical
they can go back and forth?
Yeah, they can go back and forth. Okay, but that's what it says. That's what it says. Okay. They're allowed to reverse, right? That's what going down means. That
So-
they were going up and then they're going
When you
backwards.
say at one time they have to be going the same speed,
Yes.
can it be at, so in the same, like at 8:45, they'll be going the exact same speed?
Exactly. Yeah. There's going to be some time here, right? So this is the hour, right? This is 1 o'clock, right? 1 o'clock. This is 2 o'clock, and this thing indicates your position on the track, right? Position on a linear track. So this guy starts off here, and he's going forwards first, and then he's going forward pretty fast, and then he slows down, and he comes back. He starts going backwards, and then he goes forwards again, and he ends up, this far up on the same track.
So at some x value.
Yeah, at some time, it's not probably enough time, but at some time they are going exactly the same time, same speed.
Okay.
Okay. It gets weirder from here. Okay, so.
Okay.
If you don't believe that, you will believe even less the thing I'm about to say. Okay, so so here's the generalized mean value theorem that is actually the heart of L'Hopital's theorem. The mean value theorem actually gives you L'Hopital's theorem. Okay, so generalized. So it's like this. If you have two cars. Now you've got two cars, and you don't care what they do. Okay? They can do whatever they feel like. Okay? You have two cars, they can do whatever they feel like. Again, you have the same sort of conditions. Two cars on A, B. differentiable on AB and continuous on AB. And then there's actually a little bit more condition that I'm not going to tell you about. Okay, but anyway, just wait. Okay. In that case, there is a point in AB where the ratio of the instantaneous velocities equals the ratio of the average velocities. That is to say, which equals the ratio of the different the ratio of the changes in position. There will be some point where, so you look at it, you look at the average velocity of the first guy, and you look at the average velocity of the second guy, and you take the ratio of those two things. Peculiarly, maybe not so peculiarly, it's not mysterious, we can prove it. There will be some point where the ratio of the instantaneous velocities equals that ratio of the average velocities. And so maybe, I was thinking to talk about it, but I'm not going to talk about it. I won't tell you why. I won't tell you why, but so this maybe gives you a hint about L'Hopital's rule. This might give you some hint about L'Hopital's rule, because remember the idea of L'Hopital's rule is that you have some point A where the limit of f of A and the limit of f of x as x approaches A and the limit of g of x as x approaches A are both 0. So you've got these two functions. You've got these two functions that are going to 0 there, f and g. Right? And so let's just pretend that f of A is 0 and g of A is 0. F of A is 0 and g of A is 0. Okay. Maybe you start to see L'Hopital's rule here, right? L'Hopital's rule says something about, as B goes to A, right? As B goes to A, f of B over g of B, the limit of f of B over g of B is the same as the limit of f prime over g prime. Right? The limit of f over b turns out to be the limit of f prime over g prime. Right? Okay. So let's go back. Okay. So today we're talking about L'Hopital's rule. Right? And it says this, right? If you have f and g, right? Right, so under some conditions, well, let me write them out. F and G differentiable on some interval, and the limit of f of x as x approaches c, and the limit of g of x as x approaches c are both 0. Then the limit of f of x over g of x as x approaches c equals the limit of f prime x over g prime x as x approaches c. Okay. So again, the picture is you've got this point, and you've got two functions that head to 0 there, f and g. And you're looking at the limit of the ratio. You're looking at the limit of the ratio. It turns out that the limit of the ratio is the limit of the ratio of the derivatives. Right, and you see that actually is pretty closely related to this mean value theorem, right? To the mean value theorem. Okay, so Okay, so let's just do some examples to start off with. Make you guys up. Okay, so you're not ready yet. So what do we have here? We've got natural log over x squared minus 1. You know, x is going to 1, natural log of 1 is 0, x squared minus 1 goes to 0, right? And so what do we get? Somebody just tell me. What's the derivative of a natural log? 1 over x. 1 over x, and on the bottom? 2x, right? And so what do we get? As x goes to 1, we end up with a half. Okay. Another example, the limit as e to the x minus e to the minus x over x as x goes to 0. Somebody tell me, what do I get? Right, again, we've got 1 minus 1, that's 0 over 0. Right? And so what's this? What do you get when you differentiate the top? E to the x plus e to the minus x over 1, of course, right? And then as x goes to 0, we get e to the 0 plus e to the 0, so that's 2. Right? Okay. How about the limit of the natural log of x over x to the 1/2 as x goes to infinity? So remember we said that c can be plus or minus infinity, and that you could have it also L'Hopital's rule also works when both of these guys are plus or minus infinity, and they need not be the same sign. So x is going to infinity. We've got ln x is going to infinity, right? And x to the 1/2 is also going to infinity, right? Ln x, sorry, my hand motion was wrong. Ln x is going to infinity, and x to the 1/2 is also going to infinity. Okay, right? And so the question is sort of who's going to infinity faster, right? Because you get infinity over infinity. Well, you know, if ln x is going faster, goes really quickly to infinity, then this thing is going to blow up, right? It's going to become huge, right? If the denominator goes to infinity faster, then you're going to go to 0. If they go at a ratio, if they end up being basically the same speed, you're going to get a number, right? You'll get some multiple. That one is a multiple of the other. Okay, so take 10 seconds or 20 seconds and calculate what happens. Okay, 10 seconds and fast. Who can tell me what it is? What happens? Well, what happens? Tyler, how about you? How about you, Tyler?
Okay, so 1 over x.
1 over x and
1 over 2 root x.
so 1. I'm going to write it like this. Okay. I'm going to write it like this, just for that. Okay. 1/2 x to the 1/2 minus 1.
Okay, so you'll have 2 minus x to the 1/2 minus 1 over x.
So what? Say it again, Sam. So we've got this 1 over x, and we're dividing.
So you don't have 1 over.
Okay, I'm going to put the 2 on top. Okay, and then I've got 1 over x, and I'm dividing that by x to the 1/2 minus 1. So I'm going to end up with 2 over x to the 1/2. Right? Because I bring down that x to the 1, and I've got an x to the 1/2 and x to the minus 1. The x to the 1 and the x to the minus 1 get rid of each other. Kill each other off, is what I was going to say.
So
right? And so as x goes to infinity, what happens? What happens? You get 0, right? You get 0, right? Okay. So who was faster, natural log or x to the 1/2? X to the 1/2, right? Okay. Suppose I take x to the 0.00000001 as x goes to infinity. Who can tell me right now what's going to happen? What wins? What's this going to be? Is the natural log going to win? Is natural log going faster, or is x to the 0.000001 going faster? Who can tell me right now? Thinking about what we just did, what's going to happen when you differentiate the bottom? Taylor.
It's gonna go to 0 because when you differentiate the top and the bottom, you're gonna get some number at the top, or the bottom's gonna have infinity and then the top is not gonna have infinity.
Yes. So what's going to happen, right? L'Hopital's rule. Again, we're going to get 1 over x, and again we're going to get x to this power minus 1. We're going to get this. So we're going to get. I'm just going to call this number p. Okay. Okay, so we get p x p minus 1. Right. P x p minus 1, and what happens? Right. Again, we're going to get 1 over p, x to the p minus 1, but plus 1 again. We get p again. Right. We bring down the 1. We bring the x down here. Right. That's x to the 1. Again, the x to the 1 and x to the minus 1 kill each other off. Right. And we get this. Right. And as x goes to infinity, you get 0. Right. Right. P is this tiny number, but it's bigger than 0. Okay. And so what do you see? That the natural log is actually slower than any power, right? If I took, x to the 0.00000000000, no matter how many zeros, 1, and then try to compare these things, that's still going to beat natural log. In other words, natural log is a very slow function. Natural log is a very slow function. Just like we said last time, right? The limit of e to the x over x to the hugest power, some gigantic power, e to the x is always going to win, right? Right? Because e to the x, when you differentiate it, it's not going to change. When you differentiate this guy, it's going to eventually you're going to get a constant on the bottom, right? So this is going to be infinity. E to the x beats any power, and the natural log loses to any power, right? Right. E to the x is very fast, and natural log is very slow. And thinking that they are inverses of each other, maybe that makes sense, right? Because e to the x is going up like this. Natural log is its reflection, right? If e to the x is going quickly, then natural log of x, being the reflection of it, is going to be something very slow. Okay. Any questions so far? Okay. L'Hopital's, the reach of L'Hopital's rule can be extended to things which are called indeterminate forms. So, indeterminate forms. And they're usually notated 0 to the 0, 1 to the infinity, infinity to the 0. Okay. None of these things make sense in and of themselves. Okay. Rather, they're used to describe something. So things that need to be puzzled out. Okay, so here's the first example. The limit of x to the x as x goes to 0 from the positive side. Okay, so this is something like a 0 to the 0 form. Okay, so you got x to the x, right? So x is going to 0, right? And you think like this. what would happen if we took the limit of the base first? If we said we let the base go to 0 first, and then the power go to 0, what would the limit be? If the base, we start off, we let this x go to 0 first. What's our answer? 0, right? Because you're going to have 0 to some power, that's just 0, right? Okay, now suppose we let the power go to 0 first. Suppose we let the power go to 0 first. Then it would be 1, right? Because you have some positive number to a power, to the 0 power, that's 1, right? So again, you have a competition, right? Who's going to win, the exponent or the base, right? If the base is going to win, if the base wins, then you get 0. If the exponent wins, you get 1. Okay, and let's see what happens. Okay. So the trick to extend the reach of L'Hopital's rule is to use the natural log. Okay. One uses the natural log. So you say, well, I'm not really sure what this is, but let's consider the natural log of this thing. Okay. I don't know what this thing is, but I'm gonna take its natural log, and that will allow me to use L'Hopital's rule on it. Okay. So you say, okay. Okay, so let's take the natural log, and using the continuity of the natural log, we slide the natural log through the limit. Okay? Remember, being continuous means that you can commute these things, right? You can change the order. Okay. So then what do we have? We've got natural log of x, the limit as x goes to 0 plus of natural log x to the x. That's the same thing as x natural log x, right? Because of properties of the natural log, right? You can pull the power out into a multiple, right? I'm gonna and that doesn't look so promising. It looks like what I'm doing is taking 0 times negative infinity or something, right? Because as x goes to 0 plus, natural log x goes to negative infinity. Okay, so this looks sort of like 0 times negative infinity. Okay, but let's rewrite it a little bit like this. Right, the x I'm going to change into 1 over x. Right? 1 over x is the same thing as x. Right. And now this looks more promising. It looks more like something we can use with L'Hopital's rule, because what do we have? As x goes to 0 plus, then natural log goes to negative infinity. As x goes to 0 plus, 1 over x goes to positive infinity. So now we're in infinity over infinity. We can use L'Hopital's rule. Everyone okay on the trick we played? On the tricks, we actually played 2 tricks. So to get this, to turn this thing into something that we can apply L'Hopital's rule to. Sure.
Where you got the 1 over x?
Well, I have this x here, right? So I have x times natural log x. So I'm gonna change that x into 1 over x natural log x. Okay, right? Because 1 over x is x. Okay. And you see why I'm doing it, right? It's basically I'm changing the 0 into 1 over infinity, right? This thing was 0, but I'll change it to look. I'm changing its appearance so that it looks like something I can apply L'Hopital's rule to. Okay. So then you use L'Hopital's rule, of course, right? And you get the limit as x goes to 0 plus of 1 over x over, right? -1 over x squared, right? And you see what happens. X squared comes up, and you get 0. Okay, you get 0. And so what we see, what we've just shown is that the natural log of this limit is 0. Right? The natural log of the thing we're looking for is 0. So what's the thing we're looking for? What's the thing we're looking for? 1, right? The natural log of it is 0. It is e to the 0, right? So this is going to be e to the 0. That's to say 1. Right? Natural log of the thing we're looking for is 0. That tells us that, right? That tells us that e to the 0 is the thing we're looking for, right? That's how you define the natural log. Right? If I write it like this, log base e of this thing is 0. In other words, e to the 0 is this thing. Right? Right. Okay. So watch out for that last step, because people often forget to do that last step. They calculate to here and they say, oh, it's 0, and they write 0 here. Okay. But what you calculated here was not the limit, but the natural log of the limit. Okay. Okay. Some other examples. So here that was a 0 form guy. Here's one that's 1 infinity. The limit as x goes to infinity of 1 plus 1 over x dx. Okay. So again, you have this thing, and you see that this thing on the inside goes to 1. And then the power is infinite, right? If we let the power go to infinity first, we get infinity, right? Because you've got something bigger than 1, and you're raising it to an ever-increasing power, right? So if we let the power go first, we get infinity. If we let the base go first, then what do we get? 1, right? Because you get the base would become 1, and then 1 to any power is just going to be 1, right? Okay, so again, you have this competition. You sort of a tug of war between 1 and infinity. Who's gonna win out? Okay. So who knows the answer to this? It's E. Who said it? It's E, right? So the tug of war actually balances out. One side, neither side completely wins over the other, but they balance out at the number e. Okay. So let's see that. Let's take the natural log of it. Right. Let's take the natural log of it. Actually, I'll let you do it. This is a famous thing, right? This is how we define e. I'll let you see it. Why should I show you? Why should I take that away from you? Right. It would might make me look cool or something, but so what? I don't have that need. Clearly, I have no need to look cool. Yeah, there's a danger to being a teacher, which is that you feel smart, when in fact you're not that smart. Or you may not be that smart. Maybe you are. Okay, turn to somebody next to you and say what you did or what you were doing. Okay. 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 Who would like to tell how to do it? Or who would like to just start us off? What do you do? Helen.
So you take the ln of 1 plus 1 over x plus.
Okay, so you slide the natural log in. Right. And then again you pull the exponent out. And then
I made it ln of 1 plus 1 over x over 1 over x.
right? Because if you do that, then it's in the form, right? You've got the 0 over 0 form, right? So you've got something going to 0 on the top and something that is going to 0 on the bottom, right? Then you apply the Gauss rule. What do you get when you do this?
1 over 1 plus 1 over x times negative 1 over x squared.
Times negative 1 over x squared. Is that right? Over?
Over negative 1 over x squared.
So, right, yeah. So you took the, right, you take the derivative of this thing, that's the negative 1 over x squared, and then you divide by that thing, right? Okay.
And then the negative 1 over x squared is cancelled out.
Right.
And you have 1 over 1 plus 1 over x.
And so you get 1. Those of you who are confused by this one, you've got the natural log of some function. You've got the natural log of some function, and then when you differentiate it, you get the natural log, the derivative of the natural log, right, which is 1 over x, evaluated at f of x. So you get 1 over f of x, and then you need to differentiate the inside guy. Right, so by the chain rule, you take the derivative of the outside guy, 1 over blah, evaluated at f of x, so you get 1 over f of x, and then multiply that by f prime, right? And so that's what she has here, right? This is 1 over f, 1 over the function times the derivative of the function. Right, so you end up with 1, which is good because that tells you that the limit is e to the 1. Which is e. Okay. Okay. Everyone getting the idea of this? Right. It's not that complicated. It's just if it's in one of these forms, 0 to the 0, 1 to the infinity to the 0, then you can switch it into you can change it into something that L'Hopital's rule applies to by hitting it with a natural log. Right? Hit it with a natural log and then mess around with it to make it put it in the form that L'Hopital's rule can apply to. Okay. Okay. Any questions? Emily, yeah.
What was that last step when you got from 1 to e to 7?
So at the end, right, we figure out that the natural log of the thing we're looking for is 1.
So you take natural.
So that is the same. Log base c of the thing we're looking for is 1. So the thing we're looking for is e to the 1. Okay, same trick as before. Right? I generally, I don't actually think like this. Rather, I think I've got this natural log of something. I'm going to cancel that natural log off by applying the exponential function both sides, right? Then these guys vanish, they're inverses, and so we get this thing is e to the 1. Okay, that's how I think of it. However you think. Okay, oops. So there's actually one more indeterminate form, but it's also not, it's just a algebraic trick, even simpler this time. So it's the infinity minus infinity in form. And the trick is simply that you use fractions. Okay, so you combine fractions. So you have this thing, like the least impressive trick. I guess I've done less impressive things this year, like very recently, like in the last class. But okay, this is also pretty impressive, pretty unimpressive. Okay, so yeah, maybe I should have a contest of like how unimpressive, like what's the least impressive thing I can do. Okay, so here's one. Here's a candidate, right? Okay, so you've got this thing, right? X is going to 0. Sorry. X is going to 0. You got 1 over 0 minus 1 over 0, right? In other words, something like infinity over infinity. Okay. So so what you do is you're gonna just use your elementary school knowledge, and you say, okay, I'm going to put these things together. This is going to be x minus sine x over x sine x. Okay, and now what do you have? You have 0 over 0. Okay, so now it's 0 over 0, and you can use L'Hopital's rule. Use L'Hopital's rule. That's basically it. So yeah. Okay. So right. So do you want to do it, or should I just close it there? Let's close it there. Okay. Okay. So there's 5 minutes left. That's basically it for L'Hopital's rule. Got 5 minutes. Let me show you how the generalized mean value theorem works. Okay, just for fun. I could end on something really unimpressive or something impressive. I think either way would be sort of entertaining. So you've got these two functions, you've got f and you've got g. Okay, you've got f and g, and there's nothing, you don't know anything about their distance. Okay? We're not saying this time that they end at equal distances. Okay. We actually do place a condition on g, that g prime is never 0. Okay. G prime, we want g prime never to be 0 because we're going to divide by g prime, right? We want f prime over g prime. We don't want that thing to blow up. So we're gonna say g prime never has a 0 slope. Okay. So here's the trick. You say, well, they don't satisfy, they're not the same distance apart at ends, but let's make them the same distance apart. So let's make a function alpha g. Okay, so we're going to multiply g by some number. Okay, so that, right? Let's figure out, let's create or find an alpha so that alpha g does have the same distance at the end points. So that alpha g satisfies alpha g of b minus f of b equals alpha g of a minus f of a, right? So we're going to multiply g by some number, and we're going to do it in such a way so that the difference between this new guy, the multiplied guy, and f is at b is the same as the difference at a. Okay, so let's do that. What is alpha? Well, we can figure it out, right? What's alpha? What alpha works? What alpha works? Well, we know that alpha g of b minus alpha g of a equals f of b over f of a. And so alpha is going to be g of f of b minus f of a over g of b minus g of a. Right? That's the alpha that will work for us. Okay? So if we multiply g by this alpha, we end up with a function, I don't know what it looks like, but we end up with a function that that starts and ends at the same distance from f. Okay, so that's we just saw that's the alpha we need. Okay, so what do we know then? These guys end at the same distance. So what? So there exists a point where what? These guys end and begin at the same distance from each other. So there's some point where the velocity is the same. Right? Alpha g prime c equals f prime c. Right? But what does that tell you? F prime c over g prime c is alpha. Alpha is f of b minus f of a over g of b minus g of a. And so that's the proof. That's the proof of the generalized mean value theorem that gives you L'Hopital's rule. Okay, that's it for today.